I am Assistant Professor Nilufar Yasmin from Ajay Kumar Garg Engineering College. So we'll start from where we have left. We were doing amplitude modulation and we concluded with the variations of amplitude modulation. Studying the limitations of amplitude modulation that clearly depicts that amplitude modulation or conventional amplitude modulation is somewhat inefficient in power and bandwidth conservation. We can change the forms of amplitude modulation. We can attain better level of amplitude modulation with the various formats of amplitude modulation like double sideband, suppressed carrier, single sideband and vestigial sideband. Those we discussed in little brief. So let's go through the little brief part of what we have already discussed, that in amplitude modulation, if this is how we represent the carrier wave, and this is again the definition of amplitude modulation, the process of in which amplitude of carrier wave is varied with respect to instantaneous value of the message signal or the baseband signal, and this is the general equation for amplitude modulated wave. ST equals to AC into 1 plus KAMT cos 2 pi FCT, right? So typically the carrier amplitude is represented by AC and message signal MT is measured in volts, true, right? We are going through what we have studied so far about amplitude modulation, because in this lecture we'll specifically be talking about how to generate amplitude modulation. So before that we go through what we have studied so far, right? So here Ka, this is called as amplitude sensitivity, which whose units are per volt. MT is the modulating wave, the baseband signal that carries the message. ST is the modulated waveform, with ST represents the modulated waveform. Here MT and AC are measured in volts, true, because message signal we always take as voltage signal, right? So these are the waveforms we have already discussed. Like this is how I can represent my message signal. It's a high frequency carrier wave when modulated with respect to the message signal. This kind of waveform we do get if modulation index is less than 1. If modulation index is more than 1, we get phase reversal here, right? So these are the cases of different small m modulation index, right? Now one important thing that we need to know is the envelope of modulated wave has essentially the same shape as the baseband, which is the message signal, and this is possible only when two conditions are fully satisfied. What are those two conditions? Number one condition, if the amplitude of KAMT, multiplication of this amplitude sensitivity with my message signal, that must always be less than unity. That is, mod of KAMT must be less than 1 for all t, right? It ensures that the function 1 plus KAMT is always positive, and since the envelope is positive function, why? If we get such thing, when small m is greater than 1, we get this phase reversal. We get this phase reversal, right? And this is not at all preferred in communication, right? Phase reversal is not at all preferred. So such kind of envelope is rejected. So how is it possible? When KMT is, this arrives when KMT is greater than 1. So this condition ensures that there is no phase reversal, right? And that is small m must always be less than 1. So overmodulated case is always rejected, right? The absolute maximum of this is multiplied by 100 to calculate percent modulation. That is when we represent my capital M, small m in the term in the form of percentage, capital M, right? Second condition, what is the second condition? The carrier frequency FC is much greater than the highest frequency component of the message signal. Suppose we are talking about series of message signal, not single message signal. If we are taking, if we are considering the case of multi-tone modulation, where not a single message is made to travel using one carrier, we take n number of message signals which are modulated with the help of one carrier signal. In such case, what should be the value of FC? Even in that case also, FC must be much higher than the maximum frequency content of my message signal, right? This is another condition that has to be necessarily followed to maintain the proper envelope and information within the envelope so that it exactly matches with the message signal. So these are the two conditions, right? So here W is the message bandwidth, right? From equation 3.2, which is I have named this chapter as third chapter, so equations are named as 3.1, 3.2 and so on. So this is my equation 3.2, this is my modulated message signal. So as per 3.2, we find that Fourier transform. If I want to see the spectrum, what I'll do for a time equation has to be what I do, Fourier transform to see the frequency spectrum. And when I see the frequency spectrum, I get to see that this factor get reduced by half and there is this much shift in frequency. So these are my sideband and lower sideband and upper sideband, and these two are for positive axis and negative axis, right? So this is my message frequency spectrum. This is after modulation upper sideband, lower sideband and upper sideband. This is the positive half of my wave and this shows the negative half. If I want to show it in time domain, basically we are talking about this positive half and this negative half, right? So from the spectrum, as a result of modulation process, the spectrum of message signal for negative frequencies extending from -W to 0 becomes completely visible for positive frequencies, provided that the carrier frequencies satisfy this condition, right? So that's why these conditions are important. For positive frequencies, the spectrum of an AM wave above FC is referred as upper sideband. What is upper sideband? FC plus FM or W, right? If I am referring FM, that is highest frequency content of message with small f, F subscript M or W. These are both the notations. Usually with W, we represent the complete bandwidth of my message signal, right? Below FC, it's referred as lower sideband, which can be referred as this or FC minus, right? For positive frequencies, the highest frequency component of AM wave equals this and lowest frequency component. So this appears negative for vice versa case, right? Total bandwidth of AM. If we consider the complete difference, it stands out to be this. We have discussed this. So bandwidth of AM is twice how much. If I do amplitude modulation and I need to transmit it through a channel, how much bandwidth do I require? That I can calculate from the frequency, highest frequency content of my message signal. If the highest frequency content of my message signal is, let's suppose, 10 kilohertz, then the channel bandwidth which I require for AM transmission will be 20 kilohertz, right? So let's see example number 1. If I talk about single tone modulation, single tone modulation means when I am considering one message signal and that is modulated with the help of one carrier. So this is my message signal, this is my carrier wave. Then in such case, modulated equation can be written as this, where mu is KAAM, where mu is the modulation factor or modulation index. When calculated in percentage, we call it percent modulation. To avoid over modulation, this is the condition we are familiar about. And envelope is this, right? So if I want to calculate Vmax by Vmin or Amax by Amin, that will come out to be this, right? So from here we get this formula. So modulation index can be calculated with either this formula or this formula, mu or small m, Amax minus Amin by Amax plus Amin, as discussed earlier, right? So from the formula cos A cos B, we get this expression, which are the expression for my lower sideband and upper sideband. if this is my ST, AC cos 2 pi FCT, cos A cos B is half of cos A plus B plus cos A minus B. So AC cos 2 pi FCT plus half of the external coefficient cos of 2 pi A plus B plus half of external coefficient 2 pi of A minus B, right? And when I see the Fourier transform, small s to capital S represents time domain to frequency domain conversion, which we do using Fourier transform. Then I get to see the actual spectrum, and when I see the actual spectrum, how it is with the shift, right? So I get to see the positive frequencies and the negative frequencies, right? So this holds true for my frequency spectrum of amplitude modulated waveform. This is my message signal, this is carrier, this is how I can represent amplitude modulated wave for small m less than 1, right? These are the frequencies for my message signal, for my carrier, and upper and lower sideband for positive half and negative half frequencies. I am representing the frequency peaks. So the carrier power is half AC square, upper sideband frequency power is 1/8 of, because it was already half of the coefficient already here, right? 1/4 here. So we get 1/8 of the, either we may use the notation mu or small m, represents the same thing. Lower sideband frequency power is this. So in any case, ratio of total sideband power, this plus this becomes this. It depends only on the modulation factor. So what the total power depends on what thing? The modulation index, right? So for small m equals to 1, we know that 66.66% power get wasted in carrier only. So to conserve that, we jump to double sideband suppressed carrier, right? So this is what we have discussed so far. Now go to the actual topic, what it is. We talk about AM generation. How do we generate AM? AM generation is although a simple technique that students can perform in lab as well. With the help of simple breadboard and passive components, we can generate AM. There are two classical techniques that we study here in our course, that is AM generation using square law modulator and AM generation using switching law, right? Switching modulator. So these are the two techniques. So let's start with square law modulator. It consists of these devices: a non-linear device, a band pass filter, and a carrier source and modulating signal. These are the two input signals that we provide to any modulator, that is my carrier wave and a message signal. So why non-linear device? As the name suggests, square law. Square law can be performed with the help of a non-linear device, right? We'll be needing some passive elements here. A band pass filter, of course, at generation you need a filter. Even at reception you will be needing some filters. Those will be preferably low pass filters. Although if you are using band pass filters, you can use it at generation as well as at demodulation, right? The modulating signal and carrier are connected in series with each other, and their sum is applied at the input of non-linear device. And what could be those non-linear device? We can either use a diode or a transistor. There are other devices as well. For our use, for our ease, we'll be talking about a diode. Let's see. These are the two inputs. This is my modulating signal, which I may represent as XT or MT or VT. These are the various notations you'll get to see everywhere, right? So modulating signal, and carrier is usually represented with CT, which is represented as AC cos 2 pi FCT, or here it is represented with EC cos 2 pi fct. This can be represented as am cos 2 pi fm t. Right? So these could be two oscillators. You can set one at low frequency, that will be my message signal in the range of hertz, kilohertz, right? And this you set at megahertz frequency. Combine output, which we are representing by V1T here, that goes to the non-linear device as input. And what we get as output is represented here as V2T. Then we pass it through band pass filter. Here my band pass filter is simply LC circuit, right? So sorry, it's not visible, I should stand here. So this is LC arrangement, and because of mutual induction we can get the final output load here. So this is called as load resistance, and V2 when it passes through here, the output, final output of my band pass filter, we name it as V02, and this V02 must be the wave that should be my ST, that is modulated waveform. This is a tuned circuit, tuned to frequency FC, acting as a band pass filter, right? So let's see what is my V1. My V1 is addition of my message signal and my carrier, right? This is my message and this is my carrier. Let's see, right? This is my message and carrier. And how my V1 and V2 are related? My V2 has a relation with V1 as some constant multiplied by V1 plus another constant multiplied by square of my V1. Then we can extend up to third constant and V1 cube, and but we reject these higher frequency terms, right? And we focus on these two terms only. These two terms are taken here, these are my constants, right? So let's see how I can solve this. If I expand this, my V1 is xt plus EC cos 2 pi fct from the above equation, and here again I have expanded V1 square. So in next step I'll apply a plus b whole square formula. So this is as it is noted. Here a square plus 2ab plus b square, right? Simple trigonometric formulas are applied, and when I expand it further, I do get these 5 components. What are these components? Let's see. My first component has purely my message part, xt is my message. If I concentrate on the second component, it has amplitude equal to my carrier amplitude, and if I focus on the frequency, it has frequency which is my carrier frequency. So because V2 is applied, to this band pass filter, so I must see the frequency components of my V2. And I know my band pass filter is tuned at frequency FC. That means my band pass filter will pass those frequencies which are oscillating around FC. So I should clearly see what are those frequencies that I get at V2, so that this band pass filter may pass those FC, those frequencies which are closer to FC and must reject all other frequencies. So that is why we are focusing on frequency. Here what is the frequency component? FM. Here the frequency component is FC. Here, if I expand this, this will be square of my frequency term FM. So from here, I can say it has FM frequency. Let's not talk about this. So here, I can see it has FM term as well as FC term. Here my F square of FC term. So I have to wisely choose. I have to see that band pass filter will pass which frequencies among these. As my band pass filter is tuned around FC, so this will definitely reject this frequency. This will definitely reject frequency, this frequency which is square of FC, but it will pass this frequency and pass this frequency. So I am in the next so here it is clearly depicted. Term 1 is modulating signal. This is my term 1, which is modulating signal, true. Term 2 is a carrier signal, purely carrier signal, true. Term 3 is squared modulating signal, true, modulating signal squared. Term 4 is AM wave with only sidebands. Term 4. Let's see term 4, AM with only sidebands. What does it mean? See here, when I expand this XT, I get FM cos 2 pi FMT, and this is FC cos, sorry, not FM, cos 2 pi FMT when I expand, and this is cos 2 pi FCT. So when I again apply cos A cos B, I'll get cos A plus B plus cos A minus B. That means my fourth term will have only sidebands, that is upper sideband, where A plus B terms will give you FC plus FM, A minus B terms will give you FC minus FM. So my fourth term does contains only sidebands. And if I talk about the fifth term is squared carrier, right? So squared carrier will again be rejected. So what is selected is term 2 and 3. Let's match. Yes, we selected term 2 and 4. First will be rejected, being completely message. Second will be selected because this is carrier frequency. Third will be rejected because this is message frequency. Fourth will be selected because this is FC plus FM, FC minus FM, that is the frequencies oscillating around FC. Selected. Fourth is square of FC term, which will be very high frequency, that will be rejected. So term 2 and 4 are useful, whereas remaining terms are not useful. Let's club term 2 and 3, and these are rejected. So when I consider the useful terms only, these are unuseful, these are useful terms. The five terms in the expression V2 are as under. Oh, we just discussed. So hence output voltage V0 T contains only the useful terms, carrier frequency and the sideband part, or I can rewrite this as the expression, right? When I expand it further, do trigonometric operations and comparing, I finally get ST equals to EC into 1 plus M XT cos 2 pi FCT. This is my modulation index. And does this matches with the modulating signal which we have considered initially ST? Yes, true. So my ST is EC into 1 plus M. M is my message modulation index. So my message signal cos 2 pi FCT. So this is about square law modulator. So here we can see what we are doing. We are giving two inputs, my message and my carrier, and passes through a nonlinear device and then passes through a band pass filter. We select the useful components and we reject the unuseful components, and finally what we get is my modulated waveform, right? So that's it for today. Thank you so much.